Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by SWAYAM. In the last few sessions, we had discussions on different types of flip-flops, and we have already seen that flip-flops are used as memory elements in the sequential circuits. During this session, we are going to see the applications of the sequential circuits and how these circuits are built using flip-flops. One of the well-known application of sequential circuit is register. Now, we are going to see about registers in detail. Registers are widely used in every digital systems and computers. What is a register? A register is a group of binary storage cells used to hold binary information inside. The register is a sequential circuit because the storage of the information is achieved using the flip-flops. A group of flip-flops constitutes a register. Each flip-flop can store one bit of information. So, an n-bit register can store n bits of information. Apart from the flip-flops, the registers contain combinational circuit to perform other data processing tasks. In short, registers are circuits having flip-flops to store data and combinational circuits to process that data. Here, processing implies the transfer of data, when the transfer should be done and how it should be done. On this aspect, the registers are classified into different types. And the first type of register we discuss here is buffer register. It is the simplest kind of register. All it does is only store a digital word of n bits. It is also called as register with parallel load. What is meant by parallel load? Parallel implies that some tasks happen at the same time or simultaneously at one instant of time. The term load in this context implies the loading of new information into the register. So, the parallel load signifies the loading of new information into the register simultaneously. Suppose we have an n-bit register, then we do loading for all the n flip-flops at the trigger of a clock pulse. At this trigger, each flip-flop will have a value stored inside it. As I said earlier, the buffer register only stores the values inside it. No other processing occurs. Look at this diagram. Here you can see 4 D flip-flops. Each one has an external input, the 4 binary values B0 to B3. They are fed into the register through these flip-flops. Note that all the flip-flops are controlled by the same clock pulse CLK. Having the same clock pulse will enable all the flip-flops to be triggered at the same time. Here, you must recall the difference between the level triggered and edge triggered flip-flops, which we discussed in one of the previous session. The registers can be designed in both manner, as it is a group of flip-flops. The group of flip-flops responding to the pulse duration or the level of the clock pulse is known as a latch, and the group of flip-flops responding to the pulse transition or to the edge of the clock pulse is known as register. In this session, we are going to discuss only about registers and registers which are edge triggered. Let us come back to the diagram. The circuit has 4 inputs B0 to B3. The circuit has 4 outputs too, Q0 to Q3. You can see that each flip-flop has an output. This circuit uses D flip-flops. According to the characteristic table of D flip-flop, when you give an input, the same value will be obtained as the output. That is, when D equal to 0, Q will also be 0, and when D equal to 1, Q will turn out to be 1. So, as per this, the output Q0 to Q3 will be the same value of its corresponding input. or in simple words, the output is equal to the input. So, what does this circuit do? As it receives the clock pulse, it loads the input values and transfers it to the output. And the values loaded in the current clock pulse will be retained till the next clock pulse in the circuit. In a nutshell, a buffer register transfers the input SH to the output and holds the value inside it till the next trigger. Here we used 4 flip-flops and so a 4-bit buffer register. Suppose you want an 8-bit register, then you need to have 8 D flip-flops synchronized using the same clock pulse. Similarly, you can design a buffer register to hold n bits using n D flip-flops. Now, what are the applications of buffer register? Where is it used? In digital computers, it is used as memory registers inside the processor and is accessed while reading from or writing to the main memory. These registers used inside the memory are known as memory buffer registers or MBR and provide faster access to the data stored inside it. Now, let us move on to the next type of register known as shift register. What do you mean by shifting in this context? I will give you an example. You would have used calculators to perform some arithmetic operations, right? Have you noticed how the calculator reads the input from the user? Suppose you want to input a 4-digit number 1, 2, 3, 4. Then you will be pressing the button 1 and then button 2. When you press the button 2, what happens? The value 1 in the display is shifted to left and give the unit's position to 2, so that the number becomes 12. This process continues for 3 and 4 also till you finally see the number 1234 in the display. So, when we type a number digit by digit, we are shifting each to the left before and getting ready to receive the next. This is a context where shifting has to be used. There are other applications of shifting too inside the computer while performing the arithmetic and logic operations. Now, think about the direction of shifting in this example. The digits were shifted to left. Using a different logic, we can make the bits to shift to the right also. The registers which does the left shifting is known as shift left registers and the right shifting of bits is done by shift right registers. Now, let us learn how shifting is carried out in registers. Consider a 4-bit register. As given in the diagram, initially the register content is 0, 0, 0, 0, that is Q equal to 0. Now, you have an input 1. Then in the shift left register, the word becomes 0, 0, 0, 1. What happened exactly? The stored bits moved one position to the left, which caused the leftmost 0 to be dropped and the rightmost bit to be empty. To this vacant place, the external input is stored. What happens when the next external input is 0? Then the shift left register shifts one more position to the left. The leftmost 0 is dropped and then Q becomes 0, 0, 1, 0. If the next input is 1, the Q becomes 0, 1, 0, 1, dropping the leftmost 0 again, and any time an input comes, the shift left register shifts one bit to the left. The vice versa happens in the shift right register. When an external input comes in, it shifts one bit to the right and the leftmost bit becomes vacant and the input takes its place there. See how Q, which was initially 0, 0, 0, 0, becomes 1, 0, 0, 0 when the external input is 1. Then, when the input is 0, it becomes 0, 1, 0, 0. In the next cycle, when the input is 1, the Q becomes 1, 0, 1, 0. So, whenever a new value comes as input, it shifts one bit to the right. Now you learned how shifting to left and right happens in the registers. And a register capable of shifting its binary information to the right and to the left is known as shift register. A shift register consists of a chain of flip-flops connected in cascade. And remember, all these flip-flops will receive a common clock pulse. To continue with, these shift registers operate in 4 different modes. What are the 4 modes? First one, serial in, serial out, known as SISO in short. The next, serial in, parallel out, known as SIPO. Then the third one is parallel in, parallel out, PIPO in short. And the last one, parallel in, serial out, called as PISO in short. Let us try to understand what this is all about. The term in indicates input and the term out indicates output. The terms serial and parallel indicates how data is fed into the registers and how data flows out of the registers. In serial input mode, the output of one flip-flop is connected to the next flip-flop as the input and thus enabling the serial input transmission. In parallel input mode, each flip-flop receives different external inputs. In serial output mode, there will be only one external output which is obtained from the last flip-flop connected in the circuit. But in serial output mode, each flip-flop produces an external output. Let us see each one in detail. We will start with serial in, serial out register. This is the logic diagram of a SISO register. There are 4 flip-flops chained together and there is only one external input to this register. That is, the input is supplied to the first flip-flop and the output of that register is connected to the input of the next flip-flop, and this chain continues to the next flip-flop and so on. Finally, the output of the last flip-flop of the chain is considered as the external output. Let us work out an instance of shifting a 4-bit word to this register and see how it shifts the bits. In the table given here, you can see a shift right register which shifts a value to the right on trigger of a clock pulse. Note that the same clock pulse is applied to all the flip-flops so as to ensure that they all get triggered at the same time. We proceed further with an assumption that this is an edge triggered register and on the rising edge of the clock, the register shifts the data. The data input is a 4-bit word 1010. Initially, the contents of all the flip-flops in the register are 0. On the edge of first rising clock pulse, the rightmost bit 0 is fed as the input to the register. The first flip-flop stores it and the contents of register will be 0000 itself, even though the leftmost 0 is a data bit. On the second rising edge of the clock, the second rightmost bit 1 is fed into the register. What happens now? The first flip-flop which has a 0 as its output is fed to the second flip-flop and stores the new input 1 inside it. In effect, the 0 in the first flip-flop is transferred to the second flip-flop and the value of the register will be 1000. In the third rising edge of the clock pulse, the next bit 0 is fed to the first flip-flop. What happens now? The bit 0 gets loaded in the first flip-flop and the value already inside the flip-flop gets transferred to the consecutive flip-flops. So, now the output of the register is 0100. And in the fourth rising edge, the first flip-flop has 1 inside that and the rest of the values inside the register gets shifted, resulting in 1010 in the register. So, it took around 4 clock pulses to store the value inside the register, and if we have to shift this value to another shift register, How many clock pulses may we require? Yes, another 4 clock pulses to shift these 4 bits to another shift register. Here also it must perform the identical operations to shift the value as we have seen while loading the data to the register. Look at the table. The content of each flip-flop at the rising edge of subsequent clock pulse while loading the register with the 4-bit word 1010 is summarized. See the rows 2 to 5 in the table. In the last 4 rows, the table shows how data inside the register is obtained as the output. See, to get the 4-bit data word as a whole output, you need to have neither 4 clock pulses. So, around 8 clock pulses are required to load the values from one register to the next register. So, to load a serial in serial out shift register with a 4-bit word, it took 4 clock pulses, and to shift it to another register 4 more clock pulses were needed. So, we can generalize that to shift an n-bit word to another register, we need at least 2n clock pulses. This throws light to the fact that the serial operation is comparatively slower. So, definitely our next objective is to do this shifting at a faster pace. One more point you should note here is that the SISO register can perform the left shift and right shift of values. So, you can construct a serial in serial out left shift register and a serial in serial out right shift register too. IC 7491 is a popular 8-bit serial in serial out register used in digital computers. Let us see the next type of register, serial in parallel out register. In this shift register, the data is fed in serial manner, but the output is read in parallel mode. So, this is going to save the clock pulses and will make the output availability faster than the serial in serial out register. Let us see how it is done. Look at the diagram of the SIPO register. What difference you can make out from the SISO register? The external outputs are more in number instead of a single output. We have 4 external outputs. The input is same as SISO, that is because the input mode in both the registers are the same. So, we should concentrate on the difference, how the output is produced to know about the SIPO register better. In the beginning, the register is initialized with Q as 0000. Now, if we want to load the register with a 4-bit data word 1010, what will be the procedure in SIPO register? The rightmost bit of the data word is fed into the register. The first flip-flop at the rising edge of the clock will store that value and the output Q1 will produce the same value as its output. Please note that the output of the flip-flop is connected as the input to the second flip-flop. Next, the second rising edge of the clock has come. Now, the external input will feed 1 into the flip-flop 1 and it will reset its previous value. The second flip-flop will have a 0 inside it now, which got transferred from the first flip-flop. Simultaneously, the output at Q2 will also display the value which is stored by the second flip-flop. So, at this stage your 2 bits of external inputs are set. Now, at the third rising edge of the clock, the next bit in the input is fed inside the register. Now, Q1 turns out to be 0, Q2 will be 1 and Q3 will be 0. And similarly, for the fourth rising edge of the clock, the whole data word enters into the register and is now available at its outputs Q1 to Q4. With just 4 clock pulses, now the data is readily available at the outputs. Also, there is one more advantage to this type of registers. They are capable of converting the serial data to parallel data, which is a useful characteristic for many of the operations inside a digital computer. The table shows how the values are shifted in the shift register and how it will be available in the external output. When compared with the SISO register, which took around 8 clock pulses for loading and transferring the data, the SIPO register could accomplish the same task in 4 clock pulses. So, if we generalize, an SIPO register requires n clock pulses to load to and shift an n bit data from the register. The last point about the SIPO register, only write shift SIPO registers are commonly used in the digital systems. Now, it is time to wind up the session. Let us have a quick recap. The registers were introduced in this session, which is a sequential circuit containing flip-flops in a cascaded manner. We discussed about the left and right shift registers and also the different modes of entering data to and exiting data from the registers. And in detail, we discussed about SISO and SIPO registers. In the next session, we will try to understand PIPO and PISO registers, and we will learn about the concept of universal and bidirectional shift registers. Okay friends, thank you for watching. See you in the next session. Bye.